All right, in this example, I'm bringing in the kind of math problem that health experts is working with. And I mean health experts. It could be medical doctors. It could be just scientists who work in maybe for in our nation it's the CDC people. Okay. So the wording say during the first couple weeks of a new flu outbreak, like similar to our coronavirus that's currently going on right now. Okay. But sadly, this study is not for the coronavirus. I hope they had something like this for the coronavirus, so we can find a way to contain it. But so during the first couple weeks of new flu outbreak, right, the disease spreads according to the equation I of t, so that's infections, the amount of infections right there, equals to 4,000 times e to the 0.05 t. Okay, so again, I here represents the number of infected people, and t is the number of days after the outbreak was first identified. Just like so similar to the situation of the coronavirus that we have already seen so far. It's just like I said again, sadly, I don't know no one has given me, or I didn't have time to collect data to find out about the outbreaking equation for the coronavirus. But this is a similar story right there. Okay, so now it is not our job to find out how this equation came about, because again, we leave that for the medical experts, for the healthcare, for the health experts, health professionals. What we see here is we take their modeling function, so which is now in math expression here 4,000 infected patients multiplied with e to the 0.05 t. Yeah. Okay, and so just a little bit of understanding for anyone in case you actually decide to go into the health science field right there, then this thing is it's a growth. Okay, it's a growth. It's a growth in the number of infections, and so this amount right here is called the initial amount. That 4,000 right there is called the initial amount. This value 0.05, and it's an exponential function, and that's why many scientists, they refer to this kind of growth in general as an exponential growth. This whole problem is referred to as exponential growth. Okay, but and this specific little number attached to the t inside of the exponential part here is referred to as the growth rate. Okay, it's indicating how it's only a factor that's indicating how fast the growth is going to decide how fast the growth is going. And then since it's a positive value quantity here, the whole problem is an exponential growth. So very similar. It could be a different problem where this rate right here has a negative sign. It's going to make the population decrease like that. It's called an exponential decay. But so now here, that's again just my optional explanation for you in case any viewers here after studying about these rate of change and find your passion to apply math into the medical field or into the health science field like that. So now back to the question we are asked. Find the rate at which the infected population is growing after 9 days. See, so the I letter in our problem here is the number of infected people. Okay, that's what the I is for. So our modeling function represents how big this number of infected people is growing in t days after the outbreak was first identified. And so now specifically we just want to find a rate, okay, at which the infected population is growing 9 days okay, after the outbreak. And so the rate in our understanding is simply just it's the rate of change, and it's in here it's the rate of change of the rate how fast or how slow this number of infections is going up, right, over time. So it's a rate of change, and specifically in our calculus understanding, it's an instantaneous rate of change again. It's not the same constant rate. It could be growing faster and faster every day, like that. And so in that way, now all we do is simply find the derivative. And our goal here, is once we found the general derivative, our goal is to find I prime at at 9. It's 9 days after the outbreak was identified. Okay? And so now, observing our function and realizing that it's an exponential function with the 4,000 here as being the coefficient, constant coefficient, and it's exponential function, and quite a simple exponential function in the end. Even though the value here is a little, the decimal is a little bit of decimal, but it's not so bad. Okay, so I prime here is going to give me, the derivative rule says we keep the constant coefficient, so it's 4,000 there. Okay, so and in this function itself, there's a little bit of inside here, right? So back in my lectures when I was teaching about how to find the derivative of an exponential function, and this function here gives me outside function is going to be the same e to the 0.05t repeated, because the derivative of the outside, see, the outside is the e to the something function, and then here's our inside. Our inside is here, so now I'm going to multiply with the derivative of the inside. Chain rule set that. And so now we're going to multiply with 0.05 as the derivative of the inside. All right, so now altogether, our final general rate of change of this infections right here is going to be, so 0.05 times 4,000. That value gives me 200 according to my calculation. And now raised to the power e to the 0.05t. Okay, so that's our general derivative function. And so now we're ready for getting to our goal right here. Find this particular instantaneous rate of change 9 days after the outbreak was identified. So we simply just substitute 9, because t in this problem is t. Okay, is in days, how many days there are. So 9 means 9 days. 9 here is 9 days. So 200 multiplied with e to the 0.05 times 9 here. Okay, and so now I'm going to spend a minute here doing a calculation, and let's find out what that value is. All right, and I only need 2 decimals. Now, when you're actually doing your different applications out there, then watch out from the indication from the supervisor about how far you round your calculations, okay? But here in my calculation, I'm just gonna, for this lecture, I'm just gonna round at 2 decimals only. So it's 313.66, okay? The problem itself wants you to pretend like you are an actual health expert itself. So let's select what should be the appropriate unit right here, okay? So here we're looking at what? The infection, the I itself here means the number of infected people. Okay, so that's indicating how many people, right? And our time here is in days, or here t is in days. So now clearly speaking, our appropriate units for this should be what? We gonna right on the 9th day, right on the 9th day, okay? Or maybe the 10th day because it's 9 days later, okay? The infection is growing at that many people per day. Okay, so 9 days later, which could be on the 10th day right there, counting from, because time 0 is on the first day actually. So on the 10th day, it's 9 days later. So we're at what? The infection is growing quick. So that's pretty quickly, right? 313.66 people per day, but that only the rate on that day, on that 10th day right there. All right.